Good morning, everyone. My name is Paola, and I am from the AHH Colombia chapter, and I want to welcome to our third cycle of groundwater talks. We really appreciate your support to our chapter and to join us today. I want to share with you the following link when you will find our talks schedule, and also here on the screen, and I am sharing the schedule that we have for this week. Today we will have our talk with Dr. Nils, and I want to show you some tips. So please, during the presentation, you can feel free about to write the questions on the channel, and also at the end we will have some minutes for questions. We will appreciate that you please fill our survey that I will share with you on the chat once we finish the talk. So today we will have the presentation, groundwater producing and storing thermal energy for sustainable heating and cooling by Dr. Nigel Harton from the Water Research Institute. So he works in the field of environmental geology, and particular topics of interest are groundwater quality and remediation, management aquifer and research, and geothermal production and energy storage. So welcome, Dr. Nils, to this talk, and now you can share your screen.
Okay, thank you, Paula. Let's see if this works. And go. Does this work?
Yes, it's working.
Okay, nice. Shall I start?
Yes, you can start.
Okay, thank you, Paula. Okay, hello, everybody. From wherever you are in the world. This is very nice to be able to give a presentation on geothermal production and storage. It's nice to have this link with Colombia. I checked, it's about 20 hours flying to Bogota from Amsterdam. So this is a lot smoother and more pleasant. So maybe we should also keep doing this after the Corona crisis, although I can't wait to meet some of you in Brazil in September at the IH conference. All right, so geothermal storage and production. This is a photo, and I don't know, Paula, if you recognize this from the little clues. This is a photo from Colombia. As I was doing the research for this presentation, I found out that it's not just very hot in Colombia. In some places, sometimes it can be quite cold as well, with a hailstorm in 2017 in Bogota. So my name is Niels Hartog. I'm a principal scientist of the team Geohydrology at KWO Water Research Institute. Also associated with Utrecht University, and I'm the current president of the IH Netherlands chapter.
Sorry, Dr. Nigel, could you please try to just show just one screen? Let's try because we can see the both screens. I mean,
you can see both.
No,
Let's
both
see.
the screen. No, sorry. We can see the next slide and also the current slide. So
Let's see. And now you're not seeing both?
yeah, yes, both slides. Right. The next one.
Let's see. Sorry about that.
Yes, now it's fine. Thank you so much.
Yeah, I didn't really solve it. I just pulled the plug, but nice that it works now. All right, so here we were. There we go. My name is Niels Hartog, Principal Scientist, Team Geohydrology, KWR Water Research Institute. The shareholders of that institute are the Dutch drinking water companies, so that's where our roots are. I'm also associated with Utrecht University. And this is what I look like without headphones on. All right, so in the field of hydrogeology or geohydrology, we're very used to working in the subsurface with groundwater and having attention for either the risks for groundwater quality, groundwater availability, but also how we can use the subsurface for usefully. And one of these examples is managed aquifer recharge, particularly aquifer storage and recovery. I know many of you are familiar with that, using the subsurface to make water availability more sustainable. And this has quite some links with the geothermal storage and production that I'll be talking about. So that's why I'm showing it. Where are we coming from that we started working on this geothermal field, which is still relatively new for many. Before I go on, I just want to show that I'm not doing this by myself. We have a very nice team. And in these Corona days, it looks strange to see people standing so close to each other. Actually, this is a very recent photo, 2nd of February, just before this Corona crisis hit the Netherlands. And we were fully unaware. Well, I'm looking forward to get see them in real life again. But a lot of people in this team are working on this geothermal storage and production. And I should point out Martin Bloemendaal, who about 8 years ago started together with me doing this research in this group. And now more and more people are joining us. Maybe some familiar faces for you, maybe Pieter Stuyvesant, maybe you know him from some MAR conferences. Anyway, geothermal. And I started thinking of when I saw the presentation of Daniela yesterday, I was still wondering how I would start telling this story. There's a lot to tell, and I know I cannot tell everything, but how to start this story. And Daniela showed the hydrological cycle, which I think is very nice. I thought that's what I'm going to use to connect with the previous talk and to enter the talking about energy. Because what Daniela did not emphasize, and it's logical, she was looking at the hydrological cycle as it cycles, but it's driven by solar energy. And that's a difference. Energy is not circular, water is. And by itself, the hydrological cycle is fully sustainable. So if people start talk about making the water cycle sustainable, the natural hydrological cycle is already sustainable. We can become more sustainable in how we produce and not contaminate and how we clean up the water. But the natural hydrological cycle is already sustainable, fully powered by solar energy. And we can work with this natural hydrological cycle in our field of geohydrology to make our water consumption, production more sustainable. And managed aquifer recharge is one of these techniques to make water more sustainable. But the question that really we started working on 8-10 years ago was, with all that groundwater knowledge, geohydrology can we also contribute to making this sustainable energy transition possible? And so that was the setup for how I wanted to talk about this topic today, is to first talk about heating and cooling demand. What is it? How does it vary? Some of the techniques for geothermal production and storage. Want to go into storage efficiency just because we spent quite some time on that. It's one of our focus points, and I want to work on that a little bit more, and then some reflection and conclusions. And by then, I hope even people that don't have a background in this topic to have given you a good basis of what's happening in this field and a perspective on what we're working towards, and maybe some perspective for you on how you can start working in this field as well. So let's start off with illustrating the importance of heating and cooling. I mean, there's a lot of energy used for many different things. And even though this is a relatively older diagram for the EU, the figures vary, but say 30 to 60% of the estimates for heating and cooling demand, depends on how you calculate it, are used for heating and cooling purposes, either industrial or in buildings and households. So it's really a big part of the total energy consumption. And so if we are working towards sustainable society, sustainable with respect to energy, then heating and cooling is really an important aspect to make more sustainable. So this is Martin Bloemendahl. He did his PhD 2 years ago. And this comes out of one of the papers that were a chapter in his thesis. The heating and cooling demand is not the same everywhere in the world. I think this is something that we all realize. It depends on which climatic zones we are in. And Martin made an overview and an evaluation of different kind of cooling and heating demands, and in an assessment on how aquathermal energy storage could be of use. Now you see the Netherlands here in this circle here. It's temperate climate with mild summers and a bit colder winters, and Colombia having mainly a cooling demand. And for people from the other countries that are watching, this is very generalized, of course, in cooling and heating, but this is the general picture. But heating and cooling demand is really not determined by climatic zones. It's much more determined of where the people live. So you can have a high climatic zone with a lot of cooling demand in the desert, but if there are no people, you don't actually have a cooling demand. So what I did was get a database for cities in the world and plotted the minimum monthly temperature, so that's the average minimum monthly temperature, and plotted it against the maximum monthly temperature, just to get an idea of the different cooling and heating demands in different cities in the world. So this graph needs a little bit of explanation. There's the dashed line for the 22 degrees. We can set that as the wanted indoor temperature. So if it's colder outside than 22 degrees, then we need heating. If it's warmer outside than 22 degrees, we need cooling. And you see here, the Netherlands, Amsterdam, the minimum temperature around 4 degrees Celsius, and the maximum monthly temperature around 18 degrees. And of course, there's diurnal variations during the day, and there's hot days and less hot days. So these are averages, but it gives an indication. So you also see a lot of scatter, of course. That's due to the different temperate zones that the areas are in. But you can say on average that the cities plotting below that 22 degrees line have a net heating demand. So heating demand is dominant. And contrary, you have a cooling demand for cities that have an average temperature both the minimum and the maximum above 22 degrees. Of course, if you want to have 23 degrees or 25 degrees, then it changes a little bit. So I looked a little bit at Colombia to see, and well, Paula, if you want to respond, if you see errors, please let me know. This is the indication that I got for Colombia. And actually, I learned something here. I think in Colombia, close to the equator, it's all hot, but of course, Bogota is quite high up. So there's a heating demand. So, but it's so the minimum and maximum temperature are quite the same in the year. But of course, that's the seasonal variation. And if you look at the variation during the day on a smaller time scale, not seasonal, then there's still variation in the temperatures and also in the heating and cooling demand automatically.
Actually, Bogota is not very, I mean, it's around over the night, maybe 8 degrees. I mean, and during the day could be like 22. So then the heating demand is not too much, but in comparison to Barranquilla and Medellin that are warmer than Bogota, right? Bogota needs more heating than those cities.
It's nice to hear from you, Paula, because that reminds me that there's people listening, because that's the strange thing about presenting in this way. But yeah, I can totally follow what you're saying. Actually, these graphs that I skipped a little bit quickly, the bottom one is for Bogota, and it shows that the minimum temperature varies between 5 and 9, and the maximum temperature is around 20. So that matches with what you're saying. So yeah, it depends a bit on which time in the day it's cold, whether you need heating or not. So that's the variation. All right. So these are the aspects, and this is very rough on a global perspective. What the heating and cooling demands are and how they vary. So they vary with latitude, but also with elevation. And so what kind of techniques do we have for providing heating and cooling demand? And there's a whole range of different kind of techniques, from shallow geothermal techniques down to deeper geothermal techniques. There's production of geothermal energy, and there's storage in the subsurface of thermal energy. And I'll start with the deep because that's the most developed historically. This is an image from Iceland. As you know, it's very cold up north. There's a net heating demand. We can be sure of that. And also, it's a very volcanically active area. So there's relatively high temperatures, not so deep, a steep geothermal gradient. And the temperatures are high enough not to only produce heat, but also to produce electricity. And actually, in this picture, there's the two primary energy sources for the planet Earth shown. That's the solar energy on the right hand, and then there's the geothermal energy. And all the other energy forms are derived from that. But these energies are not available constantly everywhere the same. It depends on where you are on the Earth, whether you have a high geothermal gradient that you can use, and of course, depending also on the seasons and other aspects, how much solar energy you're getting. So this is the variation on the right-hand side of the geothermal, say, potential, the heat flow density, and well, not surprisingly, like here in Italy, a hot zone, and Iceland is quite red here. These are the countries where geothermal heat production developed first. Italy was first in the world in 1902 with the first geothermal system. And well, the Netherlands, which is a small spot here, It's only 300 kilometers from north to south. Even for the small country of the Netherlands, there is variation in the geothermal potential. But we have to go already quite a bit deeper than in Iceland or parts of Italy. 2 kilometers depth, we have about 80-90 degrees Celsius water. And it's mainly the greenhouse sector that started this development. And this is just a sketch of showing in the Netherlands 2,000 meters depth, pumping up hot water 80-90 degrees, getting it through a heat exchanger, so the heat can go to the houses or to the greenhouses, and that cooled down water 30-40 degrees is pumped back into the reservoir in a different location, and in that way you can use heat without burning gas, what is typically the alternative in the Netherlands conventionally. And in the reservoir, these two, the production well and the abstraction well, are 1, 2, 3 kilometers apart, and at the surface they are much closer together, like within 10 meters. And this is a picture on what it looks like. And you see, of course, the hot well where the hot water is pumped up is insulated, and the well in the back is the cold well where the water is returned to the reservoir. So that's just an indication for some of you who maybe not be familiar with geothermal systems. And because these geothermal systems cut through the more shallow fresh groundwater, of course they could pose a risk to that groundwater. So that's something that we look into, how to do that in a good risk managed way. So like I said, the geothermal heat is mainly used for greenhouses. They kickstarted this development of geothermal systems about 10 years ago in the Netherlands, mainly using it to make all the flowers, or quite a number of the flowers that normally grow under other conditions, tomatoes, these kind of things. We're slowly moving into providing heat for cities using district heating networks, but of course in other parts of the world you can also think of cooling networks, and actually also in the Netherlands more and more we're looking into cooling networks, not just because of global warming, but for many aspects there's cooling capacity needed. So if we go more shallow, we don't have these high temperatures, but still we use geothermal, and it's like deep geothermal. It's a form of mining, because pumping up groundwater and then using a heat pump to create on one side of the heat pump hotter water. So you pump up 15 degrees Celsius groundwater and you make it 50 or 60 degrees. And then on the other end of the heat pump, you make colder water and you inject that. Or in the other way around, if you want to have cooling capacity, you pump up 20 degrees Celsius groundwater. And then, or actually, what I'm saying is for this system, there's the groundwater heat pump. Sorry about that, groundwater heat pump. So you actually pump up groundwater, and here on the left-hand side is not an open system. You're not pumping groundwater, but these are tubes. These are polyethylene tubes through which water is pumped, and heat exchange with the surrounding, the thermal energy is exchanged. One of the points of attention for these kind of systems that are just mining thermal energy from the subsurface, from groundwater, is the development of these thermal plumes. So if you have a net cooling demand in using a heat pump, and a heat pump is just an air conditioning, it's the same kind of principle. If you're pumping up groundwater using a heat pump to create cooling capacity, and then you're re-injecting the hot water that you create doing that back in the aquifer, you get a hot plume. And if the groundwater flow velocity is fast enough, that doesn't bother so much. With the re-injection well, you're pumping up the groundwater, then you have the heat pump and the hotter water you're injecting and the cooler water you're using to cool your building. But if your neighbor downstream wants to also use this system, then it becomes less efficient, because the one-up gradient is heating up the groundwater. So it's nice for one system, but if you want to make the whole energy transition for a city, then you need to prevent this kind of negative impacts. And this is what the top view looks like. This is a study from Spain, a city of Barcelona. Is re-injecting using it for cooling capacity, so re-injecting the hotter water, the water above 15 degrees Celsius, what's the natural temperature there, and temperatures up to 30 degrees. So you can imagine that other potential users of the groundwater for this cooling capacity have less efficient conditions. And the same is for the closed systems. So that is something to look into. And now my beautiful city of Utrecht. We have these summers and these winters. I don't have to explain which is winter or which is summer. Too bad we cannot enjoy the terraces at the moment. Hopefully soon. But in the winter time we need heating, and in the summertime we're complaining that it's hot. That's the way we deal with it mostly now. But it would be nice to use the winter cold for cooling in the summertime. Now, and Utrecht is not alone. Here's Amsterdam again, and well, depending on where you are, you can look at this from that perspective, using the heat from the summer to heat in the winter time, and then using the cold from the winter to cool in the summertime. But then you need some storage, and you can store it in the subsurface. So that's where you can look at combining seasonal heating and cooling. And this is the building of KWR, the one that the picture was taken in front of the team that I showed earlier. And we have one of these seasonal ATES systems. And this is what I just described in words, in a figure, pumping up cool groundwater in the summertime and going it through the building heat exchanger for cooling, and that water heats up. And in the wintertime, you reverse it. But you see already that the temperatures that I'm showing are quite low. So pumping up 8-degree groundwater is enough to cool down a building in the summertime. But if that makes 12-degree groundwater, I cannot heat up my building to 22 degrees with that in the wintertime. So here is a heat pump also that upgrades that 12-degree to 40 to be able to make the building 22 degrees. I'll come back to that heat pump a little bit later, but this is the current legislation framework in the Netherlands. You cannot go above 25 degrees injection, or you can, but only in pilots so far. And so that puts a limit on the temperature. And there's another requirement, is that you have enough this equal amounts of storage of cold and heat, so that if you lose from the storage, then you lose both heat and cold, and it's balanced, so you don't get a net heating or a net cooling of the subsurface, to prevent that others cannot use it in the same way. And it would be nice to maybe have said that the KWR building is the first, but actually they started already in the early 90s. And it's grown exponentially, and I must admit that the research was lagging behind. So these systems were being developed because the building requirements required more and more sustainable buildings. And then only in the early, well, maybe late 2000s, 2005, 2010, research started on these systems. How to make it more efficient, what's the impact on groundwater quality, etc. And you see with the dots here, and this is already an older map and also the graph, there's now already 3,000 of these type of systems in the Netherlands. And you can imagine with this density, mainly in the cities, that they start to influence each other. The volumes range quite a bit. Most systems are in the range of 100,000, 200,000 cubic meters per year storage, and they can be dealt with just one, with a double A, so two wells. And if you want to store more, then of course you need more wells to create more pumping capacity. So this is Utrecht in winter time. And with all these ATES systems in the subsurface, this is what it shows, like how they interact with each other. This was sorry, Martin, name spelled wrong. Martin Bloemendaal's PhD thesis work, looking at this interaction. And for a long time, we thought that this interaction would be negative, but since it grew organically, that people positioned their hot well also on the side where others put their hot well, and the cold well with a cold well, it proved actually that they keep each other insulated and more less losses. So actually that's one way to make the system as a whole, the sum of all these systems, more efficient. But all these systems have to be balanced in terms of cold storage and heat storage, so they don't cause a net heating or cooling. But now let's go back to this heat pump that is being used. So in the wintertime, when the 12-degree water is pumped up, the heat pump requires quite an amount of electricity to make the 40-50 degree that you need for heating the building. And when you're cold, you just want the building to heat up, and you take the electricity that's available. And we know that sustainable sources of electricity, solar and wind, are variable. So this causes, depending on using this heat pump, will take quite some, say, gray, conventional produced electricity by gas burning or coal burning, for example. So to develop more on the path of sustainability, this is using the heat pump in this way is more sustainable than directly burning gas, but there's still a big jump to make if we don't use this gray electricity for the heat pumps anymore. So we started developing, looking at that and considering using solar heat or PV panels on the building itself to create sustainable heat or green electricity, and creating cooling capacity with a dry cooler. And we developed this, cannot go in detail, ATES triplet, then you need three wells, different storages, and you can have 3 different temperature levels, and you have this buffer storage with intermediate temperatures if you cannot directly make the high temperatures that you need. So that's that for, and this really made quite a reduction of the total energy use. So from conventional burning gas in the Netherlands, mainly gas, some electricity, to a conventional double with a heat pump already gives quite a reduction in energy use, but going to a triplet will reduce it even more. And for the CO2 emissions, that jump is even bigger. So you see, even with this heat pump ATES system, as it is used now conventionally, these 3,000 systems, there's still a large potential to reduce that CO2 emissions even further. Doesn't anything increase then with the triplet? Yes, of course, there's much more pumping. So there's much more pumping between these different wells. So that gives some extra electricity used for the pumping, but since the heat pump is the biggest electricity consumer in that conventional ATES system, that doesn't make the system less efficient. Okay, so we're now already in the piloting, developing a system from low temperature ATES to high temperature ATES for a greenhouse, where they stored hot water, but it was not in balance, and now we're moving towards taking out the heat pump, developing green sustainable heat to be used, and going to high temperatures of 60 degrees. And we use DTS, distributed temperature sensing, fiberglass in the field. These are field data that you're looking at to closely monitor how the temperature is behaving, where it's going, and also doing groundwater quality analysis to see what the impact is on the groundwater quality. So now I'd like to talk about storage efficiency. I see I still have some time. So if you make an effort to store sustainable thermal energy, you want to get back as much as possible. And you also want to understand what determines how much you can get back. And that's what we call the thermal recovery efficiency. How much of the energy that I store can I get back? And then we started looking at which processes, and that's all the case with thermal aspects. The subsurface conduction losses are important. They are driven by the temperature difference between what you store and what's on the outside. And there's displacement losses because you have flow. You can have flow, and that can impact how much you can recover. We consider dispersion losses. And for the low temperature systems, we don't need to consider buoyancy losses. So the losses you get from different densities of the water. Hot water is less dense than the cooler water around it. But for the higher temperature systems, that's an aspect. So we were surprised to realize that these were not really structurally investigated, how these different processes contribute to losses in these ATES systems. So if you simplify the storage volume of thermal energy in a cylinder, so the height of the cylinder is the filter length, and then the injected water creates the cylinder. Then depending on how much volume you inject, you have a certain ratio between the area on the outside of the cylinder, on the sides and on the top and the bottom, and how much volume, so the area over volume. And that's a good measure for how much surface you have over which the heat that you store can be conducted and can be lost. And so this area over volume in this graph is relatively high for small volumes and becomes smaller with increasing volumes. And the optimum is somewhere, the optimal well screen length is somewhere in between there. And that optimal well screen length increases obviously with larger volumes. So you can calculate, and actually that's quite straightforward, then with the filter length and the thermal radius. So the heat or the cold that you inject is retarded with respect to the water you're injecting. So you have a thermal radius that is smaller than the hydraulic radius. Well, if you have that ratio between that filter length and that thermal radius of 2, then you have the optimum ratio. So that's something you can use to optimize these storage systems. And to simplify this a little bit more, we call this the pancake domain. So you have relatively small well screen lengths. So you have a pancake type cylinder. And if you have very long well screen length for a certain volume, you get more the candy stick geometry. I'll go a little bit quicker through this because you can read this back also still after the presentation. But this is maybe something you can do after the presentation. Go to your cupboard because what I just told you about the storage is already known from packaging industry. How can we package as much as possible with the least amount of material? Of course, this is the same kind of evaluation. And so from this perspective, the can on the right is probably most optimal. But packaging experts tell me that there's more to it than just this ratio, marketing, etc. What was nice to discover was that this area over volume, if we plot it against this recovery efficiency, relates relatively relates linearly with this A over V. So this is really a good measure for these kind of systems, not just in the modeling, but also in field systems that we analyzed. However, if we have flow, if we introduce flow in these simulations, so these are the crosses for 50 meters per year, we lose that nice linear correlation. So that's when we started looking into this effect of groundwater displacement on recovery efficiency. And if this is from the top view, the cylinder, you're looking at the top at the injection time, and then with groundwater flow, it is displaced every time when you want to recover it, then this is the area that is recovered. Yeah. So if you do some trigonometry, you can calculate how these relate to each other. And well, if we have the thermal radiance over this velocity, so the bigger the volume that we inject is, the bigger the radius, and the smaller the groundwater velocity, the greater this ratio and the higher the efficiency. However, if you have relatively small thermal radius or a relatively high background flow, you have a low efficiency. And this red line is actually the analytical formula that we derived that from this trigonometry, and you see it plots quite well through this impact of background flow. So this is all described in much more detail in that geothermics paper. I just thought I highlight it here. So I'm getting close to the end, I think, Paula. Don't want to make you sweat. I have a couple of more slides just to reflect and sum up. Making heating and cooling more sustainable. I think groundwater can make a good contribution worldwide to help overcome the mismatch in time when heating is needed versus when cooling is needed. To start using green electricity, to use summer heat in the winter, and vice versa. We start using the heat pump on the supply side, so converting green electricity from PV, solar, or from wind into cooling capacity or into heating capacity, and store that in the subsurface. So we have fully green heating and cooling supply. It's also important to prevent these thermal plumes to make sure that we don't mess up the groundwater thermal potential. So it's much better to, if you have a cooling demand, to convert green electricity from wind into cold water with a big heat pump, and then store the cold water, and then take that green sustainable cooling supply out when you need it, rather than running the heat pump at that moment because you might not have the green electricity available. And my impression is that is being overlooked in developing this area further. So that's why I'm stressing it here. So using solar or wind electricity, green electricity to make green cooling and heating capacity. And because that is even more variable than the demand, you know, we are used to these flat lines with production of heat from geothermal, but these green electricity-based sources are much more variable. So we need storage even more. And actually, we were developing this project just to show that it's not just imaginary. We're developing this project, but the largest part of the electricity that's produced by solar PV is making hot water, and that hot water is being pumped out when the demand is there in the wintertime by residential areas. Also, part is converted into hydrogen. That's of course also another use of green electricity to make green hydrogen. All right, so finally, last slide. In the beginning of the year, I was also in the Middle East talking about geothermal, and coming to the realization also that there's also heating capacity and cooling capacity both. Many areas in the world. So how to assess what are my possibilities, very location specific, an assessment of what is cooling versus heating demand to see if you can do some between seasons or diurnal, between cold in the night and hot in the daytime. Storing hot or cold volumes, both seasonal balancing, making sure that you don't have a net heating or cooling of the groundwater. Of course, as hydrogeologists, we know we need to look at the subsurface conditions, what layers are available, what's the permeability, how many wells do we need, etc. And looking at all the available sources, geothermal, but also converting wind, electricity, solar, and or waste heat, and all that together, I think we can make a big improvement in making heating and cooling more sustainable using groundwater. Thank you much for your attention. This is the photo again from Bogota with this hail storm in 2017. If there's any questions, I'm happy to answer them now or later. I can be reached by email, Twitter, or LinkedIn, or ResearchGate. Thank you very much.
So thank you so much for your presentation, very interesting. And we have one question from Cesar Patiño. So he is asking, please, how oil and gas fields can use and include water heat transfer? Any current field examples going on?
Okay, so if I understand the question right, the question is whether oil and gas reservoirs can be used for geothermal.
Yes.
Yeah.
Water heat transfer, yes. And if you know about any field that is using right now a technology.
Okay, it's a bit hard guessing what exactly the idea behind the question is, but I'll give two answers. One is that oil and gas reservoirs, they typically run, when that operation stops for oil and gas, it's typically because there's hot water being produced. So by the time that a field becomes geothermal, it's no longer interesting anymore. So it's specifically the parts of these oil and gas fields that are not filled with oil and gas that are interesting from a geothermal sustainability point of view. That's one. The other aspect, perhaps that's the perspective, is whether old oil and gas wells can be used for geothermal. I know of examples of people doing that. The wells have not been made for that, so there can be an issue with material suitability. The steel types, whether they can deal with the high saline geothermal solution. Clogging is an issue of the examples, but these can be addressed. And one other aspect, and that's about the exchange, is putting in polyethylene tubes like this heat exchanger that are being used in the shallow geothermal applications. And of course, this is all possible. But especially these techniques based on exchange through tubes have a much lower capacity than when you're actually pumping water. So I don't know. Between these two answers, I hope there was the answer also to your question.
I think that Cesar is talking about water production from the wells, and he says water has low enthalpy energy coming from the geothermal conditions that can be used.
Let's see. I'm in YouTube now. Where's that question?
Okay. That one is the Cesar Patiño and water production. I think that are the three last questions.
I see the three comments. I don't know exactly the question, but yeah, it's low enthalpy. What I mentioned in the beginning that at higher temperatures, it's called high enthalpy, above 150 degrees Celsius, you can also produce electricity. But for the Netherlands, we should go even much deeper. But of course, in other parts of the world, this is being done. Okay, so that also answers the Harry Moses, the question by Harry Moses. I see a question by Giselle Kimura on how are thermal plumes monitored in residential ATA systems. It's a very good good question. Just as much as the science lag behind these developments, also the monitoring lag behind. So we're more and more doing that now. The only restraint mainly at the moment is that the legislation requires these ATA systems to be balanced. But that's just for the open systems. So these should not lead to net cooling or net heating. But these closed systems, the borehole heat exchangers, are not being monitored specifically. There is monitoring in the systems, but not very good. So this is something that we advocate with each system to have monitoring. Back to you, Paula. I hope that answered the question.
Yes, I think so. But also, Dr. Harry Moses is talking about the what are the conditions. So I don't know if you answered already that.
And also, what are the conditions? Yeah, so typically above 150 degrees is when you can start producing electricity with these type of systems. So what the temperature is obviously the most important condition.
Okay, so we have a last question. Can you see there? Yes. Is the last one that you have in your screen?
No.
It's from Arif Ramashai.
Oh yeah, and I see one more there. Yeah, this is about Hungary. Quite. This is from the aquifer. Okay, well I don't know what the question is there. In recharge, how did you manage to avoid clogging of the aquifer, and does it have any ways to storage efficient? Well, clogging is with everything we do with wells is an important aspect, and especially if you go to higher temperatures, then carbonate clogging or silica clogging becomes a risk that you can manage and prevent, but you need to pay close attention. Clogging itself does not affect the recovery efficiency so much. It's more the physical aspect of getting the water in and out. Paula, can you take a charge in?
Yes, it's fine. So if you want, just stop your stop sharing, and I can show you my screen because maybe it's better.
Okay. Your screen.
So,
yeah. Okay.
Yes,
I go
stop
to,
sharing.
to
Yes.
I will stop sharing. Stop share. Yes. Okay. Yeah.
So now I can share my screen, and in that way you will see better the questions. Can you see now better? So
yes, I can see.
Here we have the Arif Arif questions, and he's talking about that he made a research using geothermal energy from abandoned wells. So okay, that helps Cesar Patiño. Now Antonio Hernandez, he's asking, what is the geothermal subsurface source in Netherlands?
Well, so I described basically two. So there's the shallow geothermal, and the thermal mining is done using a heat pump. And there's the drilling to 2 kilometers depth for 80-90 degree, and these are Triassic sandstone reservoirs mainly.
Okay, so the next question that we have is Arif. He's asking, I have a question in research. How can you manage to avoid clogging the aquifer? And does it have any relation to storage efficient?
Yes, I tried to answer that question a few minutes ago, and I hope I was sufficiently doing that.
Okay, so the last question is from Paxton Albert. Have you studied the effect of aquifer heterogeneity in terms of horizontal displacement velocities?
That's a good question. Actually, we did not address this ourselves, but I know that in literature studies exist that address this aspect to see how aquifer heterogeneity affects. Well, this ideal cylinder that I showed is not so ideal in real, of course. So how the variability and heterogeneity affects the distribution of the cylinder, and heterogeneity affects the efficiency. And these studies show that it's relatively minor, also because you have the heat conduction that goes across these heterogeneities. So the heterogeneity is not of as much effect as it is for solute transport relative to thermal transport. But of course, if you have a very extreme heterogeneity, then it affects. But in general, in the sand aquifers that we use, it's relatively minor.
Okay, Dr. Niels, thank you so much for your presentation. That was the last question.
Okay, thank you very much, Paula. If anybody has other questions or people that I could have answered the questions better, please contact me and I will do my best to answer them in a good way.
Thank you. So tomorrow we will have another presentation, guys. I mean, the people that is listening right now. So we will have the third presentation of the week. So we expect that you can join us. And also here on the chat, I will just copy the link for the survey that we need that you please help us fill in. So thank you so much for everything. And I will just copy the link right now for the survey. Thank you.